This is Precalculus Section 1.2, Functions and Their Properties, Part 2. This video lesson is a follow-up to Part 1, in which we examined functions and their properties. And we left off, number 1, increasing and decreasing graphically. And here we have the function fx equals quantity x plus 3 squared. And this is the graph of that function in a t⁻⁴cx calculator. And we change from decreasing to increasing here at x equals -3. Now, one thing I didn't mention in Part 1, video lesson Part 1, which I should have mentioned, is when you're evaluating for increasing and decreasing, you have to evaluate going left to right. So evaluate from left to right. And so if we come, the function is going to be from the left, decreasing. So our function is decreasing on, meaning on the interval. We open with a parentheses, -infinity, up to x equals -3, and we close with a bracket. Now that's a little bit debatable, but we say since the function is decreasing all the way up to x equals -3, we can close that -3 with a bracket as opposed to parentheses. And the function then starts increasing on the interval, and we're evaluating again left to right, -3 all the way up to less than infinity. Now notice parentheses are going to be adjacent to the -infinity and the +infinity. There are never brackets with infinity, only parentheses. Next, we have this next function, g of x equals x squared over x squared minus 4. And so this is what the graph of that function looks like. And so again, we evaluate in a left to right direction. So we say, I'm going to write down here, the function is increasing on, meaning on the intervals of -infinity, and our critical number here is we have a vertical asymptote. We'll talk about asymptotes later, at x equals -2. And we have another vertical asymptote here, drawn in with the dotted line here, at x equals 2. So those will be two vertical asymptotes we have here, two values of discontinuity. So we're increasing all the way up to x equals -2. And then we are going to be increasing again, and I put a U for union, from x equals -2 all the way up to x equals 0. And we can close the 0 with a bracket here. And we don't say we're increasing all the way from -infinity to 0 because there's a discontinuity here at x equals -2, which really caused a break in there. And then we are decreasing on the intervals. We're going to start at x equals 0 and decrease all the way to x equals -2, or I said -2, I should have said +2. In union, we're going to increase again from greater than 2 to less than infinity. There we have it. Next, we're going to talk about the concept of boundedness. And these are four sketches of the functions we're going to consider. The first one we have is one where we don't have a boundary below or a boundary above. For example, this function here comes from negative infinity in the range, and also at the top doesn't have an upper bound, so there's no number we can give that's an absolute boundary. I mean, it's kind of confusing here because if we look at, it looks like there's a boundary here at x equals maybe 1, and I mean y equals 1 and y equals 0 maybe, but we're looking for an upper bound and a lower bound. We see neither, so we just say flat out, not bounded above, not bounded below. Now here we have a function that, like the last one, is not bounded above, but is bounded below, because this value right here that I'm underlining in red is a lower boundary. So we say this is an example of a function that's bounded below. Next, bounded above and not bounded below. We see that if we come from negative infinity toward negative infinity, we are not bounded below, but up here at y equals, maybe that's 1, we don't know what it is, we have an upper boundary, which I have this little horizontal red line segment. And then when you are bounded above and below, like I've done here with these two horizontal line segments, we just say the function is bounded. So when you say bounded, you are indicating that a function is bounded above and below. And there are three parent functions that I can think of right now that are bounded both above and below. Next, checking for boundedness. And so we have the function f(x) equals 1/2 x squared minus 5. And if we have the graph of this function, we see a lower boundary right here. So we call this function, we say this function is bounded below, and we say not bounded above. And this is a characteristic of a basic non-flipped quadratic function. Will be bounded below. Now, if we have negative 1/2 out in front, we would be bounded above and not below. Next, g of x equals 5x over 1 plus x squared. And here's a graph of that function. And we see that the function is bounded above here at x equals 1, y equals, I think, 2.5. At x equals negative 1, y equals negative 2.5. So since we are bounded above and bounded below, we just summarize that by saying this function is bounded. Okay, the next thing we're going to talk about is local and absolute extrema. Well, extrema is Latin, and it's plural for extremes. And so if we look over here at the function itself, we're looking at peaks and valleys. So peaks and valleys. Okay, so here we have what I'm circling in red here. We have relative maximums. We'll call these relative maximums. And that would be these two here. And those will be peaks. And down below, here around point Q and point S, we have relative minimums. or local minimums, they call it. So local, the word local, sometimes you'll call that relative. Okay, next we're going to look at functions. G of x equals x to the fourth power minus 7x squared plus 6x. And here's the graph of that function. And we see we have three extrema. We have local minimums here, and we have right here up above we have a local maximum. And then the next sketch will actually show what these are using the graphing calculator. We see that we have our local minimums are negative 24.1 at x equals negative 2.06 and negative 1.77 at x equals 1.6. And our relative maximum here is 1.32 where x equals 0.456. And so this one right here, these things right here are called local or relative minimums. And then this one up here is a local maximum or relative maximum. Now it so happens that this one right here that I'm circling again in red is also what we call an absolute maximum, minimum, because it is not only the local or a valley, but it's the lowest of the lowest valleys of the whole thing. And so that's an absolute minimum. And for this function, there is no absolute maximum because the function comes from infinity on the left, goes up to infinity on the right. And so all minimums and maximums, whether absolute or not, are going to be local. And so it's kind of like a Venn diagram, that all maximums are local, but not all minima, all extrema are going to be local, but not all extrema are absolute. So now let's talk about symmetry. Symmetry is kind of geometric patterning and mirroring. And so there are three kinds of symmetry we're going to look at this point. Symmetry with respect to the y-axis, symmetry with respect to the x-axis, symmetry with respect to the origin. And we're going to look at the first example in this function. We have symmetry, we have fx equals x squared. We have symmetry with respect to the y-axis, because if we draw like this red line I'm drawing here, this function reflects perfectly about the y-axis. We also say this is an example of an even function. We're going to get to that later. If functions reflect about the y-axis, they are said to be even functions. Next, symmetry with respect to the x-axis. And we have, this is actually two functions. We are symmetric about the x-axis because this function here, there's reflection, as I'm drawing with this arrow here, from below to above. But what it takes for this, it takes two functions. because you might remember from part 1 where we had the vertical line test. If we run the vertical line test on this, we will see that, I'm drawing the blue here, the vertical line touches more than once, not a function. That's why 2 functions are required. So in terms of a single function, you will not have symmetry with respect to the x-axis. It'll take 2 functions for that. The last one we're going to look at is symmetry with respect to the origin, and I like to call this rotational symmetry. And rotation at what? This is 180-degree rotational symmetry, because if we take this cube root function and rotate 180 degrees in either direction, here I'm doing this clockwise, we're going to have a repeating pattern. And this rotational symmetry, or symmetry with respect to the origin, is indicative of what we call an odd function. So all odd functions will have this kind of 180-degree rotational symmetry, or symmetry with respect to the origin. And then finally, here's an example of a function, f of x equals 2 square root of x, that has no symmetry, neither rotational 180-degree or with respect to the x-axis or y-axis, anywhere. So now we're going to look at asymptotes. And we talked earlier briefly about asymptotes when we were doing an example of increasing and decreasing. But this function is not defined for x equals -2, nor is it defined for x equals 2. And so we can sketch and represent a vertical asymptote by this little dashed red line. So this is going to be at x equals -2. And likewise over here on the right side of the y-axis we have this vertical asymptote I'm now sketching, of whose value is x equals 2. And likewise, there's something here that we call a horizontal asymptote. I'm now sketching this horizontally in red. Okay, the horizontal asymptote, I don't think I've made it very clear, is what the value of this function approaches, but in this case will not touch. It looks like, at least at the left side, it looks like it's touching, but it really doesn't. So this is going to be the function y equals -1. So we have this x equals 2 is called a vertical asymptote, which I abbreviate VA. This x equals -2 is also a vertical asymptote. And this horizontal line, y equals -1, is a horizontal asymptote, which I abbreviate as HA. And here we have a function f(x) equals x over x squared minus x minus 2, and we can rewrite this as, by factoring the denominator, x squared minus x minus 2 factors into quantity x minus 2 times quantity x plus 1. And so we know that we cannot divide by 0 in mathematics or in algebra. So we know that if either of these factors is 0, the function does not exist. So we have x minus 2 cannot be equal to 0. So therefore, solving for x and adding 2, x cannot equal 2. That is most likely going to be a vertical asymptote at x equals 2. And likewise, for this factor on the right, we also know that x plus 1 cannot equal 0. And therefore, solving for x, x cannot equal negative 1. So these will represent most likely our vertical asymptotes. And we will see this very shortly as we go to the graph of this function. And here it is. We see a vertical asymptote at x equals negative 1 and x equals 2. Okay, so VAs, we call them. Now you can see that we could do this pretty well algebraically by factoring and setting each of those factors equal to 0. It's really harder for horizontal asymptotes. We see we have a horizontal asymptote here at, I'm sketching here in blue horizontally, at y equals 0. So that's a horizontal asymptote at y equals 0. Next, end behavior. End behavior is not in this lesson how you act before you die, but it's really what the function does at the end, from the beginning, as the function goes from negative infinity all the way to infinity. And what we're looking at in this situation is to find end behavior. We're interested in the biggest terms, the highest exponent terms in both the numerator and denominator. And if we look at this first one, a, if we ignore this plus 1, we're going to end up with 3x over x squared, which simplifies to 3x over x times x. And what we have is x over x cancel. So what we end up with here, simplified, is 3 over x. So we're going to have an end behavior of 0 on either side. If we do the same type of process for the second one, we have 3x squared over x squared. And x squared over x squared cancel equal 1. And so we're going to end up with 3. And so we're going to look for 3 as our end behavior from negative infinity to infinity. We do the same process down below here. Cross out this positive 1. We get 3x squared over, 3x cubed over x squared. And what happens is that's going to be 3x times x times x over x times x. And so these x's cancel, and so we're left with 3x. And so our end behavior is going to be from negative infinity, because it's just going to be as if the end behavior, we know in the middle it's going to do something different. The end behavior is going to look like this at one end, and the other end it's going to look like this. So we know we're going to be coming from negative infinity and going up toward infinity. And so we're going to have limit notation for this that we're going to talk about. We'll say the limit as x approaches negative infinity of f of x is equal to negative infinity. And up here at the right, we'll say the limit as x approaches infinity of f of x equals infinity. So on this one on top, it's going to be the limit as x approaches infinity of f of x is going to be 0. And then here, for b, it's going to be 3. And then down here below, if we cross out this plus 1, we're going to have 3x to the 4th over x squared, which is going to simplify to 3x squared. And for that, we don't know what's going to do in between, but it's going to look kind of like a quadratic function where we're going to start high, come down like a parabola, and end high. So let's go ahead and look at the graphs and match them up here. And here we have this first one. Well, we said the end behavior was going to be 0. So this A is going to go down here for this one. And then this 3x squared over x squared plus 1, that's going to go to 3. So it's going to be this one right up here, this the upper right corner, B. This one here, C, 3x cubed over x squared plus 1 is going to start low and end high. So that's going to be C down here. The last one, 3x to the fourth over x squared plus 1, is going to start high and end high, like this one. So again, these are some functions and their properties. In our next section, 1.3, we're going to go over the parent functions of precalculus, plus a couple more that are going to be helpful to us. Good luck, and thanks for viewing.